one of the present generally conspicuous and high-level physicists, has communicated his assessment with regards to this issue. Michio Kaku, recognized for his exceptional contributions to the fields of physics, has recently affirmed that the James Webb Space Telescope has found 6 huge cosmic systems that researchers thought couldn't exist. These examinations have the potential to open up new aspects in our scientific understanding of the universe. It is subsequently interesting and worth keeping an eye on these advancements. Kaku is an exceptional figure in the scientific field, a physicist of American and Japanese legacy. He is viewed as an expert in both classical experimental physics and quantum mechanics. Unlike some more conservative and skeptical researchers, Kaku does not belong to that group and has been receptive to the astounding results of the James Webb Space Telescope mission. We are pleased that this distinguished researcher has chosen to end his silence and openly share what can no longer be denied. The excitement and nearly most entertained tone of the eminent physicist are clear in his remarks on the discovery made by the James Webb Space Telescope, communicating that this has been the highlight that has aroused his curiosity. Join us to explore the implications of Michio Kaku's discovery of these 6 massive galaxies. Kaku is a researcher who has always been willing to consider new hypotheses throughout his life. He knows that Einstein's theories of relativity and Newton's laws are inadequate to capture the full complexity of the universe. Kaku understands that the discoveries of the new telescope have the potential to enhance the scientific field, although many of his colleagues have not been able to embrace this view. It is causing concern and insomnia among proponents and opponents of quantum mechanics. However, this only provokes laughter from Kaku. The JWST has revealed the discovery of 6 massive galaxies dating back to the earliest epochs of the universe. Each of these galaxies contains more stars than our own Milky Way, despite having formed only 200 to 700 million years after the Big Bang. The team of astronomers who made the discovery has named these extraordinary galaxies universe breakers, as their existence would alter our entire understanding of the universe. Something does not fit here anymore. The theory of the Big Bang tells us that the universe was a hot mess after the initial event. The first solid objects took many millennia to form, and it took countless additional years for the objects to reach sufficient density and produce light. The formation of complex structures like galaxies was expected to happen much later. Some of the newly discovered galaxies surpass the Milky Way in size, and their enormous luminosity indicates that they were probably forming many new stars each year, whereas our galaxy forms stars only intermittently. It remains unclear precisely when the first galaxies formed. Scientists have not been able to determine this until now. The only thing that is clear is that initially there may have been only single stars or groups of stars which eventually came together to form increasingly larger structures, gradually leading to the formation of dwarf galaxies which experienced mergers and slowly evolved. According to previous theories, highly organized and massive galaxies could not have existed at that time, which raises the question of whether the universe is much older than previously believed or whether complex toroidal structures developed much sooner. This situation is challenging for conservative science, which still struggles with this model, and some areas of physics have strongly refused to accept this discovery, questioning potential errors in the age calculations. Kaku was aware of this and had this to say: "There are numerous instances of old and misleading theories that stubbornly persist due to the prominence of some researchers. Many of these theories were eventually disproven when crucial research exposed their fallacy. Hence, the key work in any science, particularly in physics, rests with the experimentalists who uphold the scholar's legitimate truth. In fact, on Earth, we have almost no knowledge of the true origins of the universe. The Big Bang theory was established in 1927 based on observations of the universe's expansion. This data led to the conclusion that the universe started from a single point and has been expanding ever since. At the time, it was challenging for people and scientists to conceive of a universe with a beginning and an end. The idea of a universe that had always existed and was infinite in time was beyond human imagination. Even today, scientists still face difficulties understanding it. However, it is important to reconsider these possibilities. These new observations do not fit at all with what scientists have relied on for a long time in the Big Bang theory. Yet, science has shown time and again that reevaluation and openness to new ideas are crucial parts of the scientific process, just as much as the confirmation of certain theories and observations. When Einstein was a child, It was believed that the stars and planets were firmly fixed in the universe, and these specific arrangements occupied a defined space. However, we now know that everything in the universe is moving. Planets orbit stars, stars move within their galaxies at many kilometers per second, and entire galaxies move rapidly through the universe, the fate of which we cannot yet even predict. Today, scientists are challenged to accept uncomfortable truths, and it is understood that theories are not just conjectures and not absolute truths until they are thoroughly tested or confirmed by exact observations. The concept of the Big Bang emerged from the realization that galaxies are moving away from each other, and this distance is relative to the distance from Earth. This observation, known as Hubble's law, suggested that the universe was expanding. For a while, components like cosmic microwave background radiation and the redshift of light from distant galaxies and other cosmological structures seemed to support this theory. However, it is important to remember that in the past, people who believed that the Earth was flat and that the Sun orbited around us also had this kind of evidence for their assumptions until incidents or technological advancements provided a clearer and more accurate picture. Right now, we are seeing a similar situation. Scientists expected the new JWST to confirm the assumptions related to the Big Bang, but instead, they have come across these 6 galaxies that seemed impossible. This reminds us that science is constantly advancing and that scientists must be open to new discoveries and reevaluate existing theories based on available evidence. Scientists use redshift as a tool to determine certain quantities in the study of the universe. Redshift, also known as the Doppler effect, refers to the change in the color of light as the light source and the observer move relative to each other. To understand this, you can imagine stopping and watching a car coming towards you. As the car moves towards you, you hear the engine getting louder. However, once the car passes you or moves away from you, the engine sound changes. This is because the sound of the engine varies as the car moves. The same is true for light. When a light source such as a distant star moves towards us, the light we see shifts towards bluer tones. Physicists have converted redshift values into speeds and distances for measurements in the study of the universe. However, it is important to note that small errors in these measurements could have significant impacts. The measurement methods previously used are currently under review, and it is interesting to see what results researchers will arrive at regarding the latest findings related to our universe. It is crucial to consider whether these results are genuinely based on redshift errors or whether some researchers are simply denying the facts. This is a question that requires thorough examination and careful review of the data and methods used in the research. As scientific inquiry advances, the discoveries made by instruments like the James Webb Space Telescope frequently challenge our assumptions about the universe. The new discovery of 6 enormous galaxies dating back to the early epochs of the universe is one such example. These galaxies, which defy conventional theories of galaxy formation, raise significant questions about the timeline and mechanisms involved in the development of cosmic structures. The James Webb Space Telescope, a successor to the Hubble Space Telescope, is equipped with advanced technologies that enable it to peer deeper into space and see with exceptional clarity. Its ability to detect light from the distant reaches of the universe provides astronomers with a window into the past, allowing them to study galaxies that formed billions of years ago. The discovery of these ancient and massive galaxies challenges existing models, which predict that such large structures should have formed much later in the universe's history. The implications of these discoveries extend beyond astronomy and into the realm of fundamental physics, compelling researchers to reassess established theories about the early universe, including the Big Bang theory, which posits that the universe began from a single point and has been expanding ever since. While observational evidence such as the cosmic microwave background radiation and the redshift of distant galaxies initially supported this theory, the discovery of galaxies that appear too mature for their age complicates this narrative. Michio Kaku, a prominent physicist known for his work in theoretical physics and popular science, has commented on these developments. Kaku, known for his ability to bridge complex scientific concepts with public explanations, recognizes the groundbreaking potential of the JWST discoveries. Unlike some of his more skeptical colleagues, Kaku embraces the idea that groundbreaking observations should prompt revisions in scientific thinking. He has emphasized the importance of empirical evidence in shaping our understanding of the universe, highlighting that theories must continuously evolve to accommodate new information. The debate sparked by these discoveries reflects the dynamic nature of scientific inquiry. On one hand, there are proponents who argue that the discovery of early massive galaxies suggests a longer timeline for cosmic development than previously thought. This perspective challenges the traditional view that galaxies develop slowly over billions of years through mergers and incremental growth of smaller objects. On the other hand, skeptics caution against prematurely discarding established models based on limited observational data. They advocate for a cautious approach, suggesting that anomalies in data interpretation or measurement errors might explain the surprising findings. Redshift, a phenomenon observed in the light emitted by distant galaxies, plays a crucial role in these cosmic investigations. As galaxies move away from Earth, the light they emit shifts towards longer wavelengths, a phenomenon known as redshift. By measuring the degree of redshift in a galaxy spectrum, astronomers can infer its distance from Earth and its speed relative to our own galaxy. This information is essential for building models of cosmic evolution and understanding the distribution of galaxies in the universe. The James Webb Space Telescope's ability to detect faint infrared signals allows it to observe galaxies that are otherwise obscured by dust and gas in the early universe. This capability is crucial for studying the formation of stars and galaxies during the universe's infancy, a period known as the cosmic dawn. By analyzing the light emitted by these distant galaxies, astronomers can trace the chemical composition of the early universe and gain insights into the processes that drove the formation of the first stars and galaxies. In addition to its cosmic implications, the discovery of these early massive galaxies raises philosophical questions about the nature of scientific progress and human understanding. Throughout history, scientific paradigms have shifted in response to new discoveries and observations. What once seemed impossible or problematic to establish theories eventually becomes accepted as new evidence emerges. This iterative process of theory, observation, and revision is fundamental to the advancement of knowledge in all scientific disciplines. The concept of a paradigm shift, as articulated by philosopher Thomas Kuhn, describes the profound transformation that occurs when anomalies in existing theories prompt a fundamental reevaluation of scientific principles. The discovery of early massive galaxies challenges astronomers to reconsider their understanding of cosmic evolution and the processes that led to the galaxies we observe today. It underscores the importance of remaining open to revolutionary ideas and revising theories based on empirical evidence. Cosmologists and astrophysicists are also grappling with the implications of these discoveries for our understanding of dark matter and dark energy. These elusive components, which together constitute most of the universe's mass and energy content, play a crucial role in shaping the large-scale structure of the universe. The distribution of galaxies and the rate of cosmic expansion are influenced by the gravitational effects of dark matter, while dark energy is thought to drive the accelerated expansion of the universe. The discovery of early massive galaxies places new constraints on theoretical models of dark matter and dark energy, prompting scientists to refine their understanding of these enigmatic phenomena. In the realm of theoretical physics, the discovery of early massive galaxies has sparked renewed interest in alternative cosmological models. Some theorists propose modifications to the standard cosmological model, such as the introduction of extra dimensions or adjustments to the laws of gravity, to account for the observed anomalies. These theoretical ideas challenge physicists to explore new avenues of research and develop novel theoretical frameworks that can accommodate both established observations and emerging data. The JWST discoveries also have practical implications for future space exploration and the development of advanced cosmic instruments. By pushing the boundaries of observational capabilities, the telescope provides valuable insights into the technical challenges of studying distant galaxies and cosmic phenomena. It serves as a testament to human ingenuity and the collaborative efforts of scientists, engineers, and technicians who design, build, and operate cutting-edge space observatories.